Right now, somewhere in the depths of space, a star the size of our entire solar system is tearing itself apart with the force of 10 octillion nuclear bombs. You think that sounds powerful? Wait until you meet the cosmic monsters that make dying stars look like flickering candles. Black holes that devour light itself, mysterious forces ripping apart the fabric of reality, and events so violent they could erase our galaxy in seconds. If this journey through the universe's most devastating powers sounds incredible, hit that like button and subscribe for more cosmic adventures. Prepare yourselves. We begin. The surface of our sun just exploded. In the time it takes you to blink, a magnetic field line, the size of Earth, snapped like a rubber band, hurling superheated plasma into space at 2 million miles per hour. This solar flare carries the energy of 10 billion nuclear warheads, and it happened because our supposedly stable star is actually a roiling ball of controlled chaos, constantly building and releasing magnetic tension that would vaporize our planet in seconds. Picture the sun as a massive electromagnet wrapped in molten metal. Deep inside, nuclear fusion creates temperatures of 27 million degrees Fahrenheit, hot enough to strip electrons from atoms and create an electrically charged soup called plasma. This plasma moves in complex patterns, twisting and knotting magnetic field lines like invisible cables stretched to their breaking point. When these magnetic cables finally snap, they release energy equivalent to 20 million volcanic eruptions happening simultaneously. The explosion fires a burst of X-rays that reaches Earth in just 8 minutes, followed by a wave of charged particles traveling at nearly the speed of light. If you were an astronaut outside Earth's protective magnetic bubble during a major solar flare, the radiation would cook your cells from the inside out in minutes. But here on Earth's surface, we experience something far more beautiful and terrifying. The charged particles slam into our planet's magnetic field, creating the aurora borealis and aurora australis. Those dancing green and purple curtains of light represent millions of particles moving at 600 miles per second, guided by invisible magnetic highways toward our poles. The most powerful solar flare ever recorded happened in 1859, when telegraph wires sparked and caught fire across Europe and North America. Telegraph operators received electric shocks, and some telegraph systems continued working even after being disconnected from their power sources, running purely on the electrical energy pumped into Earth's atmosphere by our angry sun. Today, a flare that size would shut down satellites, collapse power grids, and knock out internet cables across entire continents. GPS systems would fail, leaving ships and planes navigating blind. The estimated damage would reach $2 trillion, and it could take years to repair the infrastructure. Solar flares follow an 11-year cycle, building to a solar maximum when our sun fires off dozens of major flares per month. During solar minimum, flares become rare, but they never stop completely. Our sun is always building magnetic tension, always preparing for the next explosive release. The strangest part? Scientists still can't predict exactly when or where the next major flare will occur. We can watch the magnetic field lines building and twisting on the sun's surface, but the moment of release remains as unpredictable as lightning during a thunderstorm. Think 10 billion nuclear bombs sound powerful? Our sun produces flares like this regularly, treating world-ending energy as nothing more than a magnetic hiccup. However, compared to what comes next, solar flares are gentle whispers in the cosmic conversation. Beneath Yellowstone National Park, a bubble of molten rock the size of Los Angeles is growing. This magma chamber sits just 5 miles under your feet if you visit the park's famous geysers, and it contains enough superheated rock to bury the entire United States under 3 feet of volcanic ash. When this monster finally erupts, it will make every volcano in recorded history look like a birthday candle. The explosion will be heard 3,000 miles away, and the ash cloud will plunge the northern hemisphere into a volcanic winter lasting years. Supervolcanoes work like pressure cookers from hell. Deep beneath the Earth's crust, Radioactive decay and gravitational pressure create pockets of magma hot enough to melt steel. Unlike regular volcanoes that build cone-shaped mountains, supervolcanoes hide their power underground, creating vast chambers that can stretch for hundreds of miles. Think of it as a massive balloon filling with molten rock under enormous pressure. The balloon keeps expanding until the ground above it can no longer hold the weight. When it finally gives way, the entire chamber empties in one catastrophic explosion that shoots debris 50 miles into the atmosphere at supersonic speeds. The Yellowstone supervolcano has erupted 3 times in the past 2 million years. The most recent explosion, 640,000 years ago, ejected 240 cubic miles of rock and ash. That's enough material to bury the entire state of Texas under 2 feet of volcanic debris. The eruption created a crater 34 miles wide and 50 miles long, which we now call the Yellowstone caldera. The eruption, 74,000 years ago at Lake Toba in Indonesia, nearly drove humanity extinct. The explosion launched so much ash and sulfur dioxide into the atmosphere that global temperatures dropped by 21 degrees Fahrenheit for several years. Archaeological evidence suggests the human population fell to just a few thousand individuals, creating a genetic bottleneck that we can still detect in our DNA today. When a supervolcano erupts, it doesn't just destroy the local area. The ash cloud spreads across continents, blocking sunlight and causing global climate change. Plants die from lack of sunlight, leading to mass starvation as crop yields collapse worldwide. The sulfur compounds create acid rain that poisonates water supplies and strips leaves from trees across entire continents. Scientists monitor Yellowstone constantly, measuring ground deformation and earthquake activity. The caldera floor has been rising and falling by several inches per year as the magma chamber below expands and contracts like a breathing giant. Small earthquakes happen daily, reminding us that this sleeping monster could wake up at any moment. The truly terrifying part? Supervolcanoes operate on geological timescales that make human planning meaningless. Yellowstone erupts roughly every 600,000 years, and we're overdue by 40,000 years. Every day that passes brings us one day closer to an explosion that could end modern civilization. But even supervolcanoes pale in comparison to the raw electrical fury that strikes our planet 5 million times every single day. A single lightning bolt just delivered more electrical power than the entire city of New York uses in 15 minutes. That flash of light lasted only 2/10,000ths of a second, yet it carried 5 billion joules of energy and reached temperatures of 50,000 degrees Fahrenheit. That's 5 times hotter than the surface of the sun, hot enough to instantly vaporize sand into glass and split nitrogen molecules in the air, creating the thunder that shakes your bones seconds later. Lightning forms when nature builds the world's most dangerous electrical circuit. Inside thunderclouds that tower 10 miles high, ice particles collide and transfer electrons, like billions of tiny generators working simultaneously. The top of the cloud becomes positively charged, while the bottom turns negative, creating an electrical difference of 1 billion volts between sky and ground. Imagine the cloud as a massive battery with positive and negative terminals separated by miles of air. Air normally acts as an insulator, preventing electricity from flowing between the cloud and ground. However, when the electrical pressure builds high enough, it overcomes this resistance and carves an invisible pathway called a stepped leader toward Earth at 200,000 miles per hour. The moment this pathway touches the ground, a return stroke of pure electrical energy rockets back up the channel at 1/3 the speed of light. This return stroke creates the brilliant flash we see, carrying 30,000 amperes of current. To put that in perspective, your household electrical outlet delivers just 15 amperes, and anything over 10 milliamperes can stop your heart. The electrical channel becomes so hot that it instantly superheats the surrounding air, causing it to expand faster than the speed of sound. This creates the shockwave we hear as thunder, which can shatter windows and damage buildings up to 10 miles away from the strike. Some lightning bolts stretch horizontally across the sky for over 100 miles, connecting multiple storm systems in a single massive electrical discharge. These bolts, called positive lightning, carry 10 times more energy than regular strikes and can jump 25 miles between clouds and ground. Ball lightning represents one of nature's strangest electrical phenomena. Witnesses report glowing spheres the size of basketballs that float through the air for several seconds after lightning strikes, sometimes passing through solid walls without leaving marks. Scientists still can't fully explain how these electrical orbs form or why they behave like they do. The most powerful lightning happens on other planets. On Venus, lightning bolts stretch across distances larger than Earth itself, while Jupiter's storms create electrical discharges 1,000 times more powerful than anything on our planet. Saturn's lightning produces radio waves so strong they interfere with spacecraft communications from millions of miles away. Every second, somewhere on Earth, lightning strikes the ground 100 times. That's 8 million strikes per day, each one carrying enough energy to power a typical American home for 3 weeks. The planet essentially operates as a massive electrical generator, constantly transferring energy between the atmosphere and ground through channels of superheated plasma. Yet, even this tremendous electrical power becomes insignificant when humanity learned to split the atom itself. The most powerful nuclear weapon ever detonated shattered windows 300 miles away and registered as an earthquake around the world. The Soviet Union's Tsar bomber released 57 million tons of TNT equivalent in a single explosion, creating a mushroom cloud that rose 39 miles into the atmosphere and a fireball 5 miles wide. The flash of light was visible 600 miles away, brighter than the sun at noon. The bomb was so powerful that its designers had to reduce its yield by half because they feared it might ignite Earth's atmosphere. Nuclear weapons work by unleashing the fundamental forces that power stars. In fission bombs, uranium or plutonium atoms split apart when struck by neutrons, releasing massive amounts of energy and more neutrons that split additional atoms. This chain reaction happens faster than you can blink, with each generation of splitting atoms releasing exponentially more energy. Think of it like a room full of mousetraps, each one balanced with 2 ping pong balls on top. Throw one ball into the room, and it triggers a trap that launches 2 balls. Those 2 balls trigger 4 traps, launching 8 balls, which trigger 16 traps, and so on. Within microseconds, every trap in the room explodes simultaneously. Fusion bombs take this concept even further by forcing hydrogen atoms together under extreme pressure and temperature, mimicking the process that powers our sun. The energy required to start fusion comes from a fission bomb used as a trigger, creating temperatures of 100 million degrees Fahrenheit in a space smaller than a baseball. The physics becomes terrifyingly elegant when you understand Einstein's famous equation. A tiny amount of matter converts to enormous amounts of energy. In nuclear weapons, less than 2 pounds of matter actually converts to pure energy. Yet this creates explosions equivalent to millions of tons of conventional explosives. Modern nuclear weapons use sophisticated designs that maximize destruction while minimizing radioactive fallout. Multiple stages of fission and fusion reactions amplify each other, creating bombs thousands of times more powerful than the weapons that destroyed Hiroshima and Nagasaki. A single modern warhead can level an entire metropolitan area and render hundreds of square miles uninhabitable for decades. The global nuclear arsenal contains enough weapons to destroy human civilization multiple times over. Countries like Russia and the United States maintain thousands of warheads, each one capable of eliminating major cities. The combined explosive power of all nuclear weapons equals roughly 1.5 billion tons of TNT, enough to excavate a canyon from New York to Los Angeles. Submarine-launched ballistic missiles can deliver these weapons anywhere on Earth within 30 minutes. The warheads re-enter the atmosphere at 15,000 miles per hour, guided by systems accurate enough to hit targets within 300 feet from thousands of miles away. The ultimate irony? Humans created these weapons by studying the same nuclear processes that occur naturally in dying stars, where gravity crushes matter so violently that atoms themselves surrender to forces beyond imagination. In the constellation Orion, a star 700 times larger than our Sun is running out of time. Betelgeuse burns through nuclear fuel at such a furious rate that it will consume its entire supply in just a few million years, compared to our Sun's 10 billion-year lifespan. When this red supergiant finally collapses, it will release more energy in 10 seconds than our Sun produces in its entire lifetime. The explosion will be visible from Earth during daylight hours for weeks, shining brighter than the full moon. Massive stars die in the most violent explosions the universe can produce. For millions of years, nuclear fusion in the star's core creates outward pressure that balances the inward crush of gravity. The star burns hydrogen into helium, then helium into carbon, carbon into oxygen, and oxygen into silicon, each fuel burning hotter and faster than the last. Picture the star's core as a series of nested furnaces, each one burning a different element. The outermost layer burns hydrogen at 18 million degrees Fahrenheit. Deeper inside, helium burns at 180 million degrees. At the very center, silicon fusion reaches 5 billion degrees, hot enough to create iron in nuclear reactions that last only days. Iron becomes the star's death sentence. Unlike lighter elements, iron fusion absorbs energy instead of releasing it. When the core fills with iron, nuclear reactions stop instantly. Without outward pressure from fusion, gravity wins the ultimate battle in less than 1 second. The core collapses from the size of Earth to the size of Manhattan in the time it takes you to say supernova. During this collapse, protons and electrons are crushed together so violently they form neutrons, releasing more energy per second than our galaxy contains in stars. The collapsing matter reaches densities where a teaspoon would weigh as much as Mount Everest. The collapse stops when neutrons themselves refuse to compress further, creating a shock wave that races outward through the star at 20,000 miles per second. This shock wave carries kinetic energy equivalent to exploding 10 octillion nuclear weapons simultaneously, ripping apart everything in its path and hurling stellar material into space at 3% the speed of light. The explosion creates elements heavier than iron by bombarding existing atoms with neutrons so rapidly that nuclear physics enters uncharted territory. Gold, platinum, and uranium form in these cosmic furnaces, along with radioactive elements so unstable they decay within seconds of creation. When the shockwave breaks through the star's surface, it creates one of the brightest events in the universe. A single supernova can outshine an entire galaxy containing 100 billion stars. The light from some supernovae travels for millions of years before reaching Earth, carrying news of stellar deaths that happened before complex life evolved on our planet. The expanding shell of superheated gas continues growing for thousands of years, creating colorful nebulae that stretch across dozens of light years. These stellar graveyards become nurseries, where new stars form from the enriched material scattered by their predecessors' violent deaths. But the crushed core left behind makes dying stars look gentle by comparison. 20 miles across and weighing twice as much as our Sun, neutron stars are the densest objects in the universe that we can actually observe. A single teaspoon of neutron star material would weigh 6 billion tons on Earth, as much as 900 Great Pyramids of Giza compressed into the size of a sugar cube. Drop this teaspoon from waist height, and it would punch through the planet like a bullet through tissue paper, creating a tunnel straight to the other side of the world. Neutron stars form when supernova explosions crush stellar cores beyond the breaking point of normal matter. The gravitational pressure becomes so intense that protons and electrons can no longer exist as separate particles. They smash together to form neutrons, creating matter so dense that atomic structure itself collapses into a solid ball of nuclear material. Imagine taking all the empty space out of atoms and packing the remaining neutrons together like marbles in a jar. On Earth, atoms are mostly empty space, with electrons orbiting far from the nucleus, like planets around a star. In neutron star matter, this empty space disappears completely, creating material 200 trillion times denser than rock. The surface of a neutron star resembles a crystalline landscape harder than diamond, with mountains that rise less than an inch above the ground despite containing more mass than Earth's entire mountain ranges. The crust is so rigid that it can support magnetic field lines twisted into complex knots that store more energy than our sun produces in a year. Gravity on a neutron star is 200 billion times stronger than Earth's gravity. If you could somehow stand on the surface, you would weigh as much as Mount Everest, and your body would be flattened thinner than a sheet of paper in microseconds. The escape velocity reaches 100,000 miles per second, nearly half the speed of light. These stellar corpses spin at incredible rates because conservation of angular momentum concentrates the original star's rotation into a sphere just 20 miles wide. Some neutron stars complete over 700 rotations per second, spinning faster than a kitchen blender while maintaining perfect stability, despite gravitational forces that would tear apart any normal object. The magnetic fields around neutron stars are trillions of times stronger than Earth's magnetic field, powerful enough to strip electrons from atoms thousands of miles away. These magnetic fields channel charged particles into narrow beams that sweep across space like cosmic lighthouses, creating radio signals we can detect from across the galaxy. When two neutron stars spiral toward each other, they create gravitational waves that ripple through space-time itself. The final collision releases more energy in gravitational waves than all the stars in the observable universe produce in visible light. These collisions forge heavy elements like gold and platinum through nuclear processes so violent they make supernovae look peaceful. The strangest part about neutron stars is that we can actually observe them, despite their small size. Their extreme density and magnetic fields make them cosmic beacons that broadcast radio signals across thousands of light years. However, some neutron stars take this broadcasting to an entirely different level of cosmic violence. Every 1.337 seconds, a cosmic lighthouse, 28,000 light-years away, fires a beam of radiation directly at Earth with the precision of an atomic clock. This pulsar, catalogued as PSR Bone 1919+21, was the first one discovered by astronomers who initially thought the regular radio signals might be messages from an alien civilization. The signals arrived so precisely that scientists briefly nicknamed the source Little Green Men, before realizing they had found something far stranger than intelligent life. Pulsars are neutron stars that have become cosmic death rays. Their powerful magnetic fields, trillions of times stronger than Earth's, accelerate charged particles to nearly the speed of light along magnetic field lines that extend thousands of miles into space. These particles emit intense beams of radio waves, X-rays, and gamma rays that sweep across space like the beam from a lighthouse. Picture a neutron star as a spinning top with two powerful searchlights mounted at opposite poles, each light beam cutting through space in a perfect circle as the star rotates. When one of these beams points toward Earth, our radio telescopes detect a brief pulse of energy. As the star continues spinning, the beam sweeps past us, and we detect nothing until the next rotation brings the beam back around. The fastest known pulsar spins 716 times per second, faster than the blades of a jet engine. This neutron star, designated PSR Joan 748-2446 AD, completes more than one full rotation in the time it takes light to travel from one side of the star to the other. The surface moves at 24% the speed of light, creating gravitational effects so extreme they slow down time itself compared to our reference frame on Earth. Some pulsars fire beams powerful enough to cook planets. The Crab pulsar, formed by a supernova explosion observed by Chinese astronomers in 1054, emits more energy per second than our sun produces in visible light. If this pulsar were located 30 light-years from Earth, its radiation would strip away our atmosphere and sterilize the planet's surface in minutes. Pulsar beams carry so much energy that they create their own weather systems in space. The intense radiation pressure blows away surrounding gas and dust, creating cavities in interstellar medium that can stretch for hundreds of light years. These bubbles contain almost no matter, creating regions of space emptier than the best vacuum chambers humans can build. The timing of pulsar signals is so precise that astronomers use them as natural atomic clocks scattered throughout the galaxy. The Pulsar Timing Array project monitors dozens of pulsars to detect gravitational waves by measuring tiny changes in the arrival time of their signals. These neutron star chronometers are accurate enough to detect when gravitational waves stretch and squeeze space by distances smaller than the width of a proton. Some pulsars steal material from companion stars, accelerating the stolen gas to such high speeds that it glows brighter than our sun, before crashing into the neutron star's surface at millions of miles per hour. Yet even these cosmic lighthouses pale before neutron stars, whose magnetic fields have reached truly terrifying extremes. The magnetic field around Magnetar SGR 180620 is so powerful it could erase every credit card on Earth from a distance halfway to the moon. This neutron star possesses a magnetic field 1 quadrillion times stronger than Earth's, powerful enough to levitate a frog from 600 miles away by diamagnetically repelling the water molecules in its body. If you could somehow approach within 600 miles of this cosmic monster, the magnetic forces would stretch your atoms into needle-like shapes and rip the electrons from their orbits. Magnetars form when the most massive stars collapse with their magnetic fields still intact. During the supernova explosion, magnetic field lines get twisted and compressed along with everything else, concentrating magnetic forces that were already millions of times stronger than Earth's field into a ball just 12 miles across. Think of magnetars as cosmic dynamos gone berserk. The magnetic field lines become so tangled and twisted that they store more energy than our sun produces in 100,000 years. These field lines act like invisible rubber bands, stretched far beyond their breaking point, constantly building tension until something has to give way. When magnetar field lines finally snap and reconnect, they release energy equivalent to multiple nuclear weapons, exploding every second for months. These magnetic earthquakes, called starquakes, crack the neutron star's ultra-hard crust and send shockwaves racing around the star's surface at thousands of miles per second. The December 26, 2004 starquake on SGR 180620 released more energy in 1/10 of a second than our sun produces in 150,000 years. The burst of gamma rays was so intense it temporarily blinded satellites, disrupted radio communications across Earth's entire daylight hemisphere, and measurably affected our planet's magnetic field from 50,000 light-years away. Magnetar magnetic fields are so strong, they change the fundamental properties of empty space itself. In the most intense regions near the surface, the magnetic field becomes strong enough to make vacuum behave like a solid crystal, bending light and creating optical effects that Einstein's theories struggle to fully describe. The surface temperature of a magnetar reaches 18 million degrees Fahrenheit, heated not by nuclear reactions but purely by the decay of magnetic field energy. This makes magnetars the hottest objects in the known universe, hot enough that they glow in X-rays for millions of years after their formation. Some magnetars fire focused beams of energy that make pulsar emissions look weak. When these beams sweep across Earth, they can deliver more radiation in seconds than our sun produces in decades. Fortunately, magnetars are rare, with only 29 confirmed examples in our galaxy containing over 200 billion stars. The magnetic field gradually weakens over millions of years as the twisted field lines slowly untangle and release their stored energy. Eventually, magnetars evolve into normal pulsars, their cosmic temper tantrums finally exhausted. But when two of these stellar monsters meet each other in the depths of space, their collision creates fireworks visible across the entire universe. Two neutron stars, each weighing more than our sun, are spiraling toward each other at half the speed of light in their final moments before collision. The gravitational dance has lasted millions of years, with the two stellar corpses slowly losing energy to gravitational waves that ripple outward through space-time itself. Now, in the final seconds, they orbit each other 1,000 times per second, their surfaces just 60 miles apart, moving so fast that time dilation effects make each second last slightly longer for the stars than for distant observers. When neutron stars collide, they create the most violent explosions since the Big Bang. The impact releases more energy than our Sun will produce during its entire 10 billion year lifetime, compressed into a burst lasting just milliseconds. The collision is so energetic that it shakes the fabric of space-time hard enough for us to detect these gravitational waves using laser interferometers here on Earth. Picture two cosmic cannonballs, each one containing the mass of a star compressed into a sphere the size of Manhattan, slamming together at 186,000 miles per second. The kinetic energy alone equals the rest mass energy of several Earths, completely converted to pure energy through Einstein's famous equation. The moment of impact creates temperatures of 1 trillion degrees Fahrenheit, hot enough to break down atomic nuclei and create exotic forms of matter that exist nowhere else in the modern universe. Neutrons get crushed into quarks, the fundamental building blocks of protons and neutrons, forming a soup of subatomic particles similar to conditions that existed microseconds after the Big Bang. During the collision, rapid neutron capture processes forge elements heavier than iron in nuclear furnaces, operating at impossible temperatures and densities. A single neutron star collision produces several Earth masses worth of gold, platinum, and other precious metals, hurling them into space at 20% the speed of light. The explosion creates a kilonova, an optical flash that can be seen from billions of light years away. Unlike supernovae that fade over weeks, kilonovae glow in infrared light for months as the newly created heavy elements decay radioactively. The distinctive infrared signature tells astronomers they are watching cosmic element factories in action. Some stellar collisions create black holes when the combined mass exceeds the limit for neutron star stability. Others form highly magnetized neutron stars, called Magnetars, inheriting twisted magnetic field lines from both parent stars. The most massive collisions might create objects so dense that normal physics breaks down completely. The gravitational waves from stellar collisions carry information about the interior structure of neutron stars, allowing scientists to study matter under conditions impossible to recreate in any laboratory. These waves arrive at Earth stretched and compressed by factors smaller than 1/10,000th the width of a proton, yet our instruments can detect them. Stellar collisions happen roughly once per year in a galaxy like the Milky Way, meaning somewhere in the observable universe, two stellar remnants are destroying each other in unimaginable violence every few seconds. However, the stars responsible for creating these neutron star bullets in the first place dwarf even these cosmic car crashes. If you place the hypergiant star Scuti at the center of our solar system, its surface would extend beyond the orbit of Jupiter. This stellar monster contains enough material to build 5 billion stars the size of our Sun, yet it burns through its nuclear fuel so wastefully that it will exhaust its supply in just 3 million years. During its brief lifetime, Scuti loses mass equal to our entire Moon every single year, blasting away its outer layers in stellar winds that race through space at 100,000 miles per hour. Hypergiant stars form when gas clouds containing more than 25 times our Sun's mass collapse under their own gravity. The resulting star is so massive that nuclear fusion in its core operates at temperatures exceeding 500 million degrees Fahrenheit, creating energy production rates millions of times higher than our Sun. Think of hypergiants as cosmic pressure cookers on the verge of explosion. The tremendous gravitational force trying to crush the star inward is barely balanced by the outward pressure from nuclear reactions, burning billions of tons of hydrogen into helium every second. This balance is so precarious that tiny fluctuations cause the entire star to pulsate like a beating heart, expanding and contracting by millions of miles over periods of months. The surface temperature of hypergiants is relatively cool at just 6,000 degrees Fahrenheit, making them appear red despite their enormous energy output. This coolness allows the formation of complex molecules in the star's outer atmosphere, creating vast shells of dust and gas that can obscure the star from direct observation. Hypergiant stellar winds carry away mass at such incredible rates that they create cavities in space larger than our entire solar system. These stellar hurricanes push surrounding interstellar gas into expanding bubbles that continue growing for millions of years after the star dies. The Pistol Star, another hypergiant, has created a nebula 4 light-years across, containing gas moving at 60 miles per second. Some hypergiants are so unstable they experience false supernovae, eruptions, powerful enough to briefly outshine entire galaxies. Eta Carinae underwent such an explosion in 1843, becoming temporarily the second brightest star in Earth's sky, despite being 7,500 light-years away. The eruption hurled material weighing 20 times more than our Sun into space at 1,500 miles per second. When hypergiants finally exhaust their nuclear fuel, they collapse into black holes without passing through a supernova phase. The stellar core becomes so massive that nothing can stop gravitational collapse, creating an event horizon that swallows the entire star from the inside out within seconds. The most extreme hypergiants may collapse directly into intermediate mass black holes, weighing hundreds of times more than our Sun. These stellar mass monsters represent missing links between stellar black holes and the supermassive black holes that lurk in galactic cores. Hypergiants are so rare that our galaxy contains fewer than 10 of them among its 200 billion stars. Their rarity makes sense, given that they consume their fuel faster than any other type of star. But even hypergiants cannot match the self-destructive fury of stars that literally blow themselves apart while still alive. WR-102 is destroying itself so violently that it loses material equivalent to Earth's mass every 10,000 years, blasting its own atmosphere into space at 4 million miles per hour. This Wolf-Rayet star burns at surface temperatures of 108,000 degrees Fahrenheit, 18 times hotter than our Sun's surface, creating stellar winds so powerful they strip away the star's outer layers faster than nuclear fusion can replace them. These cosmic hurricanes carry enough energy to power our entire civilization for trillions of years. Wolf-Rayet stars represent the final death throes of the most massive stars in the universe. After burning through their hydrogen fuel, these stellar giants begin fusing heavier elements in their cores, while simultaneously tearing themselves apart from the outside in. The surface layers get blasted away by radiation pressure, so intense it overcomes the star's massive gravitational pull. Picture a star trying to hold itself together while generating winds that would strip Earth's atmosphere away in seconds. The stellar material accelerates outward at such tremendous speeds that it glows brighter than our Sun, despite being scattered across regions larger than our solar system. These expanding shells of superheated gas create some of the most beautiful nebulae in the galaxy. The core of a Wolf-Rayet star operates like a cosmic furnace, burning elements in layers. Hydrogen fusion occurs in the outermost layer, helium burning happens deeper inside, and carbon fusion takes place near the center, at temperatures of 600 million degrees. Each layer burns faster and hotter than the one above it, creating an increasingly unstable stellar structure. Wolf-Rayet stars produce stellar winds so dense they block most of the star's light from reaching us directly. We see these stars primarily through the fluorescent glow of their expanding nebulae, like looking at a light bulb through thick fog. The Rosette Nebula and the Ring Nebula are prime examples of Wolf-Rayet stars lighting up their own stellar graveyards. Some Wolf-Rayet stars occur in binary systems, where they strip material from companion stars while simultaneously blasting away their own outer layers. These stellar vampires create complex interactions where gas streams flow between stars at millions of miles per hour, heating up to millions of degrees and emitting X-rays visible from across the galaxy. The stellar winds from Wolf-Rayet stars are so powerful They sweep up surrounding interstellar material into vast cavities called stellar wind bubbles. These bubbles can grow to hundreds of light years across and contain almost no matter, creating regions of space emptier than the best vacuum chambers humans can build. When Wolf-Rayet stars finally explode as supernovae, they create some of the most energetic explosions in the universe. Their cores have already been exposed by stellar winds, allowing the supernova shockwave to escape more easily and shine brighter than normal stellar explosions. Most Wolf-Rayet stars collapse into black holes because their cores become too massive for even neutron star matter to support. The stellar winds that make these stars so spectacular also ensure their complete gravitational collapse when nuclear fuel runs out. Yet these self-destructing monsters are merely appetizers compared to the main course of stellar destruction that follows. Supernova SN 1006 was so bright that medieval astronomers could read books by its light, even though the exploding star was located 7,200 light-years from Earth. This stellar explosion released more energy in seconds than our Sun will produce during its entire 10 billion-year lifetime, creating a shockwave that continues expanding through space at 2,000 miles per second, 1,000 years after the initial blast. The explosion was visible during daylight for months and remained the brightest star in the night sky for over 2 years. Supernovae occur when massive stars exhaust their nuclear fuel and can no longer generate enough outward pressure to resist gravitational collapse. The stellar core, now composed primarily of iron, suddenly loses structural support and collapses from the size of Earth to the size of Manhattan in less than 1 second. Think of a supernova as nature's ultimate implosion, followed by the universe's most violent explosion. During core collapse, matter becomes so dense that atomic nuclei touch each other directly, creating pressures equivalent to the weight of Mount Everest, balanced on every square inch of surface. When this ultra-compressed matter finally rebounds, it creates a shockwave carrying the kinetic energy of 10 billion nuclear weapons. The explosion accelerates stellar material to 3% the speed of light, hurling elements forged in the star's nuclear furnaces across hundreds of light-years. Iron, nickel, cobalt, and dozens of other elements get scattered through interstellar space, enriching the cosmic medium that will eventually form new stars and planets. Supernovae create elements heavier than iron through rapid neutron capture processes that occur only during these explosive events. Gold, platinum, uranium, and other heavy elements form when atomic nuclei get bombarded with so many neutrons that normal nuclear physics breaks down. A single supernova can produce several Earth masses of these precious metals. The light from supernovae can outshine entire galaxies containing 100 billion stars. Type Ia supernovae are so consistently bright that astronomers use them as standard candles to measure distances across the universe, leading to the discovery that cosmic expansion is accelerating due to dark energy. Some supernovae create neutron stars when the collapsing core stops at nuclear density. Others form black holes when the core mass exceeds the limit that neutron degeneracy pressure can support. The most massive supernovae might create black holes so large they swallow the entire explosion, producing dim stellar deaths called failed supernovae. Supernova shockwaves compress nearby gas clouds and trigger the formation of new stars, creating stellar nurseries from the ashes of stellar death. The Crab Nebula, formed by a supernova observed by Chinese astronomers in 1054, continues expanding at 900 miles per second, while the central neutron star pulses 30 times per second. The neutrinos produced during core collapse carry away 99% of the explosion's energy, racing through space at nearly the speed of light. Supernova 1987A in the Large Magellanic Cloud produced so many neutrinos that detectors on Earth recorded 24 of them passing through the entire planet. But even these galaxy-illuminating explosions become insignificant when stellar death creates beams that can sterilize planets across cosmic distances. GRB 80916c released more energy in 23 minutes than our Sun will produce in its entire lifetime, firing a beam of gamma rays across 7 billion light-years with the precision of a cosmic sniper rifle. This gamma ray burst concentrated the explosive power of several supernovae into twin jets narrower than 1 degree, creating the most energetic electromagnetic event ever observed in the universe. If this burst had occurred in our galaxy just 1,000 light-years from Earth, it would have stripped away our ozone layer and triggered a mass extinction event comparable to the one that killed the dinosaurs. Gamma-ray bursts occur when the most massive stars collapse directly into black holes, bypassing the neutron star phase entirely. As matter spirals into the newly formed black hole, it heats up to billions of degrees and gets accelerated to 99.9% the speed of light along powerful magnetic field lines. Picture a stellar mass black hole as a cosmic particle accelerator gone berserk, channeling the gravitational energy of an entire collapsing star into 2 narrow beams fired in opposite directions. These jets punch through the collapsing star's outer layers and break free into space, carrying more concentrated energy than any other phenomenon in the known universe. The gamma rays in these bursts carry individual photons with energies millions of times higher than visible light photons. Each photon packs enough energy to power a typical household for several hours, and the bursts contain trillions upon trillions of these high-energy particles racing through space in perfectly collimated beams. Long gamma-ray bursts last from several seconds to several minutes and originate from hypernovae, supernovae explosions, at least 10 times more energetic than typical stellar deaths. The collapsing star must be rotating rapidly to generate the twisted magnetic fields necessary to focus the explosion's energy into narrow jets. Short gamma-ray bursts lasting less than 2 seconds come from neutron star collisions, the same events that create gravitational waves detectable by LIGO. These mergers produce gamma-ray bursts less energetic than stellar collapse events, but still powerful enough to outshine entire galaxies for brief moments. The afterglow from gamma-ray bursts can be detected across the electromagnetic spectrum for weeks or months after the initial explosion. Radio telescopes, optical telescopes, and X-ray satellites work together to track the expanding shockwave as it plows through interstellar material at relativistic speeds. Some gamma-ray bursts are pointed directly at Earth, purely by chance, allowing us to study these cosmic blowtorches in detail. The beams are so narrow that most gamma-ray bursts in our galaxy would miss us completely, meaning we only detect the rare events aimed in our direction from distant galaxies. Scientists estimate that gamma-ray bursts occur roughly once per day somewhere in the observable universe, meaning these ultimate expressions of stellar violence are happening constantly throughout cosmic space and time. The energy scale of gamma-ray bursts represents the upper limit of what individual stars can achieve through gravitational collapse and magnetic field interactions. At the center of our galaxy lurks a gravitational monster 4 million times more massive than our Sun, capable of stretching you into a strand of atoms thinner than dental floss. Sagittarius A, our galactic black hole, warps space-time so severely that clocks run slower near its event horizon, and light itself cannot escape once it crosses that invisible boundary 24 million miles from the center. Stars orbit this cosmic vacuum cleaner at speeds reaching 12 million miles per hour, completing orbits that would take light hours to traverse in just 16 years. Black holes form when matter becomes so dense that it punches a hole through the fabric of space-time itself. The gravitational field becomes so intense that it creates a region where the normal rules of physics break down completely. At the event horizon, time stops relative to outside observers, while anyone falling in experiences time normally until tidal forces tear them apart. Think of black holes as cosmic drains, where space and time flow like water spiraling down a bathtub drain. The closer you get to the center, the faster space flows inward until the flow speed exceeds the speed of light at the event horizon. Nothing can swim upstream against a current moving faster than light itself. The singularity at a black hole's center represents a point where density becomes infinite and the laws of physics as we understand them simply cease to function. All the black hole's mass gets compressed into a region smaller than a single atom, creating gravitational effects so extreme that they might tear holes in reality itself. Stellar mass black holes form from collapsed stars and typically weigh between 3 and 20 times our Sun's mass. When matter falls into these cosmic monsters, it accelerates to tremendous speeds and heats up to billions of degrees, creating accretion disks that shine brighter than entire star clusters. The tidal forces near black holes stretch objects along the direction, pointing toward the center while squeezing them in perpendicular directions. This spaghettification effect would pull your head and feet apart with forces equivalent to hanging the entire weight of Mount Everest from each end of your body. Black holes slowly evaporate through Hawking radiation, a quantum mechanical process where particle pairs created near the event horizon result in a net loss of mass over cosmic time periods. Paradoxically, smaller black holes evaporate faster than larger ones, meaning stellar mass black holes will outlive supermassive black holes by trillions of years. Some black holes spin at nearly the maximum rate allowed by general relativity, dragging spacetime around with them in a process called frame dragging. These rotating black holes store enormous amounts of rotational energy that could theoretically be harvested by advanced civilizations. When black holes merge, they create gravitational waves that ripple through spacetime at the speed of light, carrying away energy equivalent to several solar masses converted directly into distortions of space and time itself. Yet even these reality-warping monsters appear small and gentle compared to the galactic behemoths that anchor entire star cities in gravitational servitude. The supermassive black hole in galaxy Mate 7 weighs 6.5 billion times more than our Sun and has an event horizon larger than our entire solar system. This galactic monster, officially designated Mate 7, controls the motion of stars across a region spanning 65,000 light-years, holding an entire galaxy of 1 trillion stars in gravitational bondage. The black hole's sphere of influence extends so far that light takes several hours to travel from one side to the other, making it larger than the orbit of Pluto. Supermassive black holes anchor the centers of virtually every large galaxy in the universe, acting as gravitational shepherds that control galactic structure and star formation rates across cosmic distances. The Milky Way's central black hole is actually small by supermassive standards, weighing only 4 million solar masses compared to monsters that tip the scales at 20 billion times our Sun's weight. Picture these cosmic titans as the ultimate gravitational monopolies, so massive that they bend space-time across galactic scales. Stars located thousands of light-years away feel their gravitational influence, orbiting the galactic center in complex patterns that take hundreds of millions of years to complete. The most massive known supermassive black hole, TON 618, weighs 66 billion times more than our Sun and has an event horizon with a diameter of 2,400 astronomical units. If this monster replaced our Sun, its event horizon would extend far beyond the orbit of Neptune, engulfing our entire solar system in eternal darkness. Supermassive black holes grow through two primary mechanisms: accreting matter from their surroundings and merging with other supermassive black holes during galactic collisions. When galaxies merge, their central black holes eventually spiral together and coalesce in explosions that shake spacetime across billions of light-years. The feeding patterns of supermassive black holes control star formation throughout their host galaxies. When these monsters actively consume matter, they heat surrounding gas to temperatures that prevent star formation. When they go dormant, cooling gas can collapse into new stellar nurseries, creating cycles of galactic death and rebirth, spanning hundreds of millions of years. Some supermassive black holes launch jets of matter at 99.9% the speed of light, creating cosmic blowtorches that extend thousands of light-years beyond their host galaxies. These relativistic jets carry enough energy to heat intergalactic gas and influence the formation of galaxy clusters containing thousands of individual galaxies. The The relationship between supermassive black holes and their host galaxies is so intimate that the mass of the central black hole correlates precisely with the total mass of stars in the galactic bulge. This suggests that black holes and galaxies co-evolve through processes that scientists are still trying to understand. When supermassive black holes actively feed on surrounding matter, they become visible as quasars, some of the brightest objects in the universe. The accretion disk around an actively feeding supermassive black hole can shine with the luminosity of 1 trillion stars. But when these galactic monsters enter their most violent feeding frenzies, they transform into cosmic lighthouses, visible across the entire observable universe. Quasar 3C 273 shines with the brightness of 4 trillion suns, while located 2.5 billion light-years from Earth, making it easily visible through amateur telescopes, despite being farther away than most galaxies. This cosmic lighthouse is powered by a supermassive black hole consuming matter equivalent to 300 Earths every single minute, converting the infalling material into pure energy through gravitational processes more efficient than nuclear fusion. The black hole's accretion disk glows at temperatures of 100 million degrees Fahrenheit, hot enough to emit more energy than entire galaxies containing hundreds of billions of stars. Quasars represent supermassive black holes in their most violent feeding phase, when vast quantities of gas and dust spiral inward at nearly the speed of light. As this matter approaches the event horizon, friction heats it to such extreme temperatures that it radiates across the entire electromagnetic spectrum, from radio waves to gamma rays. Think of a quasar as a cosmic bonfire, where the fuel is entire solar systems worth of matter, and the flames reach temperatures found nowhere else in the modern universe. The accretion disk around the central black hole becomes a natural particle accelerator, generating magnetic fields trillions of times stronger than Earth's, and launching relativistic jets thousands of light-years into space. The most luminous known quasar, APM 8279 plus 5255, outshines our Sun by a factor of 4 quadrillion, making it bright enough to illuminate planets orbiting stars thousands of light-years away. This monster is powered by a black hole weighing 23 billion solar masses, consuming matter at such a furious rate that it approaches the theoretical maximum feeding speed allowed by physics. Quasars were much more common in the early universe, when galaxies contained larger reservoirs of gas available for black hole consumption. Most quasars formed between 8 and 12 billion years ago, during an era when the universe was younger and denser. Today, quasars are relatively rare because most supermassive black holes have exhausted their local food supplies. The energy output from quasars is so intense that they can influence star formation in galaxies millions of light-years away. The radiation pressure and high-energy particles streaming from these cosmic monsters heat intergalactic gas, preventing it from cooling and collapsing into new stars across vast regions of space. Some quasars vary in brightness over timescales of days or weeks, indicating that their energy output changes as matter falls irregularly into the central black hole. These brightness fluctuations help astronomers measure the size of quasar accretion disks and study the physics of matter under extreme gravitational conditions. Gravitational lensing by intervening galaxies can split the light from distant quasars into multiple images, creating cosmic mirages that allow astronomers to study both the lensing galaxy and the background quasar simultaneously. These gravitational telescopes provide unique insights into the distribution of dark matter throughout the universe. When quasars exhaust their fuel supplies, they fade into ordinary supermassive black holes, sitting quietly at the centers of their host galaxies, waiting for the next delivery of matter to restart their cosmic light show. However, some quasars channel their tremendous energy into focused beams that make their total luminosity seem almost modest by comparison. The supermassive black hole in Galaxy M87 fires a jet of superheated plasma 5,000 light-years into space at 99.95% the speed of light, creating a cosmic blowtorch visible from 54 million light-years away. This relativistic jet carries the kinetic energy equivalent to our sun's total mass energy, converted to pure motion, concentrated into a beam narrower than our solar system, but longer than the distance from Earth to our nearest stellar neighbors. The jet's magnetic fields are so powerful they could strip electrons from atoms across interstellar distances. Active galactic nuclei represent the ultimate expression of supermassive black hole power, where the energy of accretion gets channeled into narrow beams that punch through galactic boundaries and extend deep into intergalactic space. These cosmic flamethrowers reshape the structure of galaxy clusters and influence star formation across millions of light years. Picture the supermassive black hole as a cosmic jet engine, where infalling matter gets caught in twisted magnetic field lines that act like invisible railguns. The magnetic fields accelerate charged particles to such extreme speeds that time dilation effects make seconds pass like minutes for particles racing along the jet compared to stationary observers. The jets from active galactic nuclei create cavities in the hot gas surrounding galaxy clusters, carving out bubble-shaped voids larger than entire galaxies. These cosmic excavations redistribute trillions of solar masses of intergalactic medium, creating sound waves with frequencies so low that a single oscillation takes 10 million years to complete. Some active galactic nuclei launch jets from both poles simultaneously, creating symmetric structures that extend for millions of light years in opposite directions. The jet from galaxy Centaurus A stretches across 14 degrees of sky as seen from Earth, spanning a distance equivalent to 28 full moons lined up side by side. When these relativistic jets point directly toward Earth, we observe them as blazars, among the most violently variable objects in the universe. Blazar brightness can change by factors of 100 within hours, as shock waves race along the jet at nearly light speed, creating lighthouse effects that flash across cosmic distances. The particles in these jets carry so much energy that individual electrons shine brighter than entire stars through synchrotron radiation. When high-energy particles spiral around magnetic field lines at relativistic speeds, they emit photons across the entire electromagnetic spectrum, from radio waves to gamma rays. Active galactic nuclei can remain active for hundreds of millions of years, fed by steady streams of matter flowing toward the central black hole. However, the jets can shut off suddenly when the fuel supply gets disrupted, leaving behind ghostly radio lobes that fade over millions of years. The most powerful active galactic nuclei influence the evolution of entire galaxy clusters, containing thousands of individual galaxies. Their energy output regulates cooling flows in the intergalactic medium and determines where new stars can form across vast regions of cosmic real estate. But individual galaxies, no matter how active their cores, eventually face an even more dramatic fate when gravity brings entire galactic neighborhoods into collision. In 4.5 billion years, the Andromeda Galaxy will slam into the Milky Way at 250,000 miles per hour, creating a cosmic car crash involving over 1 trillion stars. This galactic collision has already begun at the edges, where the outer regions of both galaxies are starting to feel each other's gravitational pull across the 2.5 million light-years that currently separate them. The approach speed seems slow by human standards, but represents enough kinetic energy to power our sun for longer than the universe has existed. When galaxies collide, individual stars rarely hit each other directly because the vast distances between stars make physical collisions extremely unlikely. Instead, the gravitational interactions reshape both galaxies completely, flinging stars into new orbits and triggering massive bursts of star formation as gas clouds compress and collapse. Think of galactic collisions as cosmic dances performed by dancers made of hundreds of billions of stars. The gravitational choreography stretches spiral arms into elegant tails and bridges that can extend for hundreds of thousands of light years. These tidal streams of displaced stars create some of the most beautiful structures in the universe. The supermassive black holes at the centers of colliding galaxies eventually spiral together in their own deadly waltz. As they orbit closer and closer, they release gravitational waves that carry away orbital energy, causing the black holes to merge in a final explosion that shakes space-time across billions of light-years. During major galactic collisions, star formation rates increase by factors of 10 to 100, as shock waves compress interstellar gas clouds beyond their normal density thresholds. These starburst events create stellar nurseries containing thousands of young, massive stars that will live fast and die in spectacular supernova explosions. The collision between the Milky Way and Andromeda will likely trigger the dormant supermassive black hole at our galaxy's center to become active again as fresh gas gets funneled toward the galactic core. Our quiet neighborhood could suddenly feature a bright quasar visible from other galaxy clusters. Some galactic collisions are so violent they completely disrupt both galaxies, scattering their stars across millions of light-years and creating diffuse stellar halos with no recognizable structure. These galactic train wrecks leave behind elliptical galaxies composed primarily of old, red stars in chaotic orbits. The antennae galaxies provide a preview of what galactic collisions look like in progress, with two spiral galaxies currently tearing each other apart through tidal interactions. Long streams of stars extend hundreds of thousands of light-years from the collision site, creating antenna-like structures visible through powerful telescopes. Galaxy mergers drive the growth of supermassive black holes by feeding them vast quantities of gas disrupted from stable orbital patterns. The merged black holes can receive kick velocities from gravitational wave recoil that eject them entirely from their host galaxies, creating wandering supermassive black holes racing through intergalactic space. Yet, even these billion-year galactic demolition derbies represent just local neighborhood disputes compared to the gravitational architecture that governs thousands of galaxies simultaneously. The Coma Galaxy Cluster contains over 1,000 galaxies bound together by gravitational forces equivalent to 1 quadrillion times our Sun's mass, creating a cosmic city spanning 20 million light-years. This galactic metropolis holds its member galaxies in gravitational servitude through dark matter halos that extend far beyond the visible boundaries of individual galaxies. The cluster's total mass is so enormous that it bends light from background galaxies, creating gravitational lenses that magnify and distort images of objects billions of light-years farther away. Galaxy clusters represent the largest gravitationally bound structures in the universe, containing hundreds to thousands of individual galaxies swimming in seas of superheated plasma, reaching temperatures of 100 million degrees Fahrenheit. This intergalactic medium glows brightly in X-rays, outshining all the member galaxies combined when observed at high energy wavelengths. Picture galaxy clusters as cosmic pressure cookers, where the gravitational compression heats gas to such extreme temperatures that it strips electrons from atomic nuclei across millions of light-years. The resulting plasma creates magnetic fields that trap high-energy particles and generate radio emissions, detectable from billions of light-years away. The most massive known galaxy cluster, El Gordo, weighs 3 quadrillion times more than our Sun and spans 15 million light-years from edge to edge. This cosmic monster formed through the collision of two smaller galaxy clusters, creating shock waves that heat the intergalactic medium to over 300 million degrees Fahrenheit. Galaxy clusters grow through accretion and mergers, constantly capturing new galaxies from the surrounding cosmic web, while occasionally colliding with other clusters in events that release energies comparable to billions of supernovae exploding simultaneously. These cluster mergers create some of the most energetic events since the Big Bang. The Bullet Cluster provides dramatic evidence for dark matter by showing the separation between visible matter and gravitational effects during a high-speed cluster collision. The normal matter got slowed down by friction during the collision, while the dark matter passed through unaffected, creating a cosmic crime scene that reveals the invisible architecture of the universe. When galaxy clusters collide, they create radio relics and radio halos that span millions of light-years, powered by shock waves that accelerate particles to nearly the speed of light. These cosmic particle accelerators operate on scales that dwarf anything humans can build, creating natural laboratories for studying high-energy physics. The intracluster medium contains more normal matter than all the member galaxies combined, yet this hot gas remains invisible to optical telescopes despite outweighing trillion star galaxies. The plasma is so diffuse that its density approximates the best vacuum chambers on Earth, yet its total mass dominates the cluster's visible matter budget. Galaxy clusters serve as cosmic telescopes through gravitational lensing effects that can magnify background objects by factors of 50 or more. Astronomers use these natural magnifying glasses to study the most distant galaxies in the universe, including objects formed less than 1 billion years after the Big Bang. But the visible matter in galaxy clusters represents only the tip of an iceberg floating in vast oceans of invisible material that controls the fate of cosmic structure itself. The dark matter halo surrounding our Milky Way galaxy extends over 1 million light-years into space and weighs 10 times more than all the visible stars, gas, and dust combined. This invisible gravitational scaffold determines where stars can form, how fast galaxies rotate, and which cosmic structures will survive the universe's accelerating expansion. Dark matter interacts only through gravity, making it completely transparent to light, while dominating the gravitational architecture that shapes everything we can see in the cosmic landscape. Dark matter halos form the hidden skeleton upon which visible galaxies grow, like ornaments hanging on an invisible Christmas tree. Computer simulations show that without dark matter's gravitational scaffolding, normal matter would never have clumped together efficiently enough to form the first stars and galaxies after the Big Bang. Think of dark matter as cosmic glue that holds galaxy clusters together, despite their internal velocities that should tear them apart. Galaxy cluster members orbit at speeds exceeding 2,000 miles per second, fast enough to escape the gravitational pull of all visible matter, yet they remain bound within invisible dark matter prisons, extending far beyond the cluster's visible boundaries. The most compelling evidence for dark matter comes from galaxy rotation curves, which show that stars in galactic outskirts orbit much faster than they should based on visible matter alone. These stars should fly off into intergalactic space, yet they remain in stable orbits within vast dark matter halos that can extend 10 times farther than the visible galactic disk. Dark matter halos contain substructure on all scales, with smaller halos orbiting within larger ones in complex hierarchical arrangements. The Milky Way's halo contains dozens of satellite galaxies and hundreds of dark matter subhalos that may once have hosted their own stellar populations before being stripped bare by tidal interactions. Gravitational lensing reveals the detailed structure of dark matter halos by showing how they bend and distort light from background galaxies. These cosmic magnifying glasses allow astronomers to map dark matter distributions with remarkable precision, revealing clumpy structures that extend across millions of light-years. The collision between dark matter halos during galaxy cluster mergers creates some of the most extreme gravitational environments in the universe. Computer simulations show these collisions generating shockwaves in the dark matter distribution that propagate at thousands of miles per second across megaparsec distances. Dark matter particles likely interact with each other through forces other than gravity, but these interactions are so weak that dark matter halos can pass through each other like cosmic ghosts during cluster collisions. The Bullet cluster dramatically demonstrates this behavior, with dark matter halos continuing their motion while normal matter gets slowed by electromagnetic interactions. The cosmic web connects dark matter halos across the universe through filamentary structures containing most of the universe's dark matter. These invisible highways channel matter flows between galaxy clusters and determine where future star formation will occur across cosmic time. Yet even the vast dark matter scaffolding that shapes cosmic structure operates within expanding voids that grow larger than the spaces between galaxy superclusters themselves. The Boötes void spans 330 million light-years across and contains almost no galaxies in a region large enough to hold 25,000 Milky Ways, side by side. This cosmic desert, also called the Great Nothing, represents one of the largest empty regions in the known universe, containing roughly 90% less matter than average cosmic density. The void is so enormous that light takes over 300 million years to cross from one edge to the other, yet this vast space contains fewer galaxies than our local cosmic neighborhood. Cosmic voids form through a process called gravitational drainage, where matter flows away from underdense regions toward areas that will eventually become galaxy clusters and superclusters. Over billions of years, this cosmic segregation creates vast, empty regions surrounded by walls and filaments of galaxies arranged in a cosmic web pattern. Picture the universe as cosmic Swiss cheese, where the holes represent voids and the cheese represents filamentary structures containing most galaxies. The voids grow larger over time as dark energy accelerates cosmic expansion, while the matter-rich regions become increasingly isolated islands in an ocean of expanding emptiness. The local void, which our local group of galaxies borders, spans 150 million light-years and explains why we see relatively few bright galaxies in certain directions. This cosmic cavity influences the peculiar velocities of nearby galaxy groups and may be responsible for the apparent motion of our local group through the cosmic microwave background radiation. Inside cosmic voids, galaxy formation becomes extremely inefficient because the low matter density prevents gravitational collapse. The few galaxies that do form in voids tend to be small, dim, and isolated, evolving much more slowly than galaxies in dense environments. These void galaxies provide natural laboratories for studying how galaxies evolve without external influences. Void expansion represents one of the most direct manifestations of dark energy's influence on cosmic structure. While matter-rich regions can resist expansion through gravitational attraction, voids contain too little matter to significantly slow their growth. This makes them cosmic expansion meters that directly measure how fast dark energy pushes space apart. The largest known void, the CMB cold spot supervoid, may span up to 1.8 billion light-years across and could explain mysterious temperature variations in the cosmic microwave background radiation. This cosmic refrigerator cools photons passing through it, creating detectable temperature differences in the universe's thermal echo from the Big Bang. Void walls, the boundaries between cosmic voids and matter-rich regions, contain some of the most massive galaxy superclusters in the universe. These cosmic intersections represent regions where multiple filaments meet, creating gravitational traffic jams that concentrate matter into the largest bound structures known. As cosmic expansion accelerates, voids will continue growing until they dominate the universe's volume. Eventually, the matter within void walls will get stretched so thin that new star formation will cease, leaving isolated galaxy clusters stranded in an increasingly empty cosmos. The expansion of cosmic voids represents just one manifestation of a mysterious force that operates on the largest possible scales to tear apart the very fabric of reality itself. Dark energy comprises 68% of everything that exists in the universe, yet scientists have no idea what it actually is or why it's ripping space apart with ever-increasing violence. This invisible force drives the accelerating expansion of the universe, pushing galaxies apart at speeds that increase over cosmic time. Distant galaxy clusters recede from us faster today than they did billions of years ago, indicating that something is actively working against gravity on the largest possible scales. Dark energy was discovered through observations of distant supernovae that appeared dimmer than expected, revealing that the universe's expansion has been accelerating for the past 5 billion years. This discovery overturned decades of cosmological theory and introduced the disturbing possibility that the ultimate fate of the universe involves everything being torn apart by an unknown force. Think of dark energy as anti-gravity that operates only over cosmic distances, becoming stronger as space itself grows larger. Unlike matter and radiation that become diluted as the universe expands, dark energy maintains constant density, meaning its total influence grows as the universe creates more space to fill. The energy density of dark energy is extraordinarily small by everyday standards, equivalent to only 6 hydrogen atoms per cubic meter of space. However, when multiplied by the volume of the observable universe, this tiny density represents more energy than all the matter and radiation combined, making dark energy the dominant component of cosmic reality. Several theories attempt to explain dark energy's nature, from quantum vacuum fluctuations to extra-spatial dimensions that leak gravitational effects into our three-dimensional space. The cosmological constant, proposed by Einstein and later abandoned, has been revived as the leading candidate for dark energy's identity. Dark energy's influence becomes apparent only on scales larger than galaxy clusters, where its repulsive effect overwhelms the attractive force of gravity. On smaller scales, gravity remains dominant, allowing stars, planets, and even galaxy clusters to maintain their structural integrity despite the universe's accelerating expansion. The acceleration caused by dark energy means that distant galaxies are moving away from us faster than the speed of light due to the expansion of space itself. This creates a cosmic event horizon beyond which we can never communicate with or influence distant regions of the universe, even in principle. If dark energy continues driving acceleration at its current rate, the universe faces a Big Rip scenario where expansion eventually becomes so violent that it tears apart galaxy clusters, then galaxies, then solar systems, and finally, atoms themselves. This cosmic doomsday could occur in 22 billion years. Alternatively, dark energy might decay or change its properties over cosmic time, leading to different ultimate fates, including cosmic collapse, cyclic universes, or transitions to entirely different physics regimes. The uncertainty reflects our profound ignorance about dark energy's fundamental nature. Current observations suggest dark energy behaves like Einstein's cosmological constant, maintaining constant density as space expands. However, more precise measurements might reveal subtle variations that could revolutionize our understanding of gravity, quantum mechanics, and the nature of reality itself. Yet even dark energy's universe-spanning influence pales before the original explosion that created space, time, and all the energy that dark energy now redistributes across cosmic scales. 13.8 billion years ago, everything that would become the observable universe occupied a region smaller than a single proton and exploded with infinite energy density. This wasn't an explosion in space, but rather the explosive creation of space itself, along with time, matter, energy, and all the physical laws that govern reality. In the first fraction of a second, the universe expanded from quantum scale to astronomical proportions, while cooling from infinite temperature to merely billions of degrees. The Big Bang created time as we understand it, making questions about what happened before the Big Bang potentially meaningless. Time itself emerged from the quantum foam during the Planck epoch, the first 10 to the minus 43 seconds when the universe was so hot and dense that our current understanding of physics breaks down completely. Picture the Big Bang as the ultimate creative act, where pure energy density transforms into the rich complexity of matter, radiation, and space-time geometry we observe today. Every atom in your body, every star in the sky, and every galaxy in the universe traces its origin back to this primordial explosion that created everything from nothing. During the first second after the Big Bang, the universe underwent nucleosynthesis, forging the lightest elements from free protons and neutrons in a cosmic nuclear reactor operating at 10 billion degrees Fahrenheit. This process created roughly 75% hydrogen and 25% helium, establishing the elemental composition that would fuel the first stars billions of years later. The cosmic microwave background radiation represents the afterglow of the Big Bang, stretched by cosmic expansion from visible light to microwave frequencies over the past 13.8 billion years. This thermal echo provides a baby picture of the universe when it was only 380,000 years old and had cooled enough for electrons and protons to combine into neutral atoms. Temperature fluctuations in the cosmic microwave background reveal tiny density variations that served as seeds for all future cosmic structure. These quantum fluctuations, amplified by cosmic expansion, eventually grew into the galaxies, stars, and planets that populate the universe today. The Big Bang theory predicts the observed abundance of light elements, the cosmic microwave background temperature and structure, and the large-scale distribution of galaxies with remarkable precision. These multiple lines of evidence provide overwhelming support for the idea that the universe began in an incredibly hot, dense state. Matter and antimatter were created in nearly equal quantities during the Big Bang, but a slight asymmetry favoring matter by 1 part in 1 billion allowed normal matter to survive after mutual annihilation destroyed most of the primordial particle pairs. This tiny imbalance explains why we live in a matter-dominated universe, rather than empty space filled with radiation. The Big Bang converted pure energy into the mass and motion we observe throughout the cosmos. Yet the total energy of the universe might actually be zero when gravitational potential energy is included in the cosmic accounting. However, the Big Bang itself may have been preceded by an even more violent epoch when space expanded faster than the speed of light itself. During the first trillionth of a second after the Big Bang, the universe expanded by a factor of at least 10 to the 26th power, growing faster than light and increasing in size, more in that instant than it has in the entire 13.8 billion years since. This period of cosmic inflation stretched space so rapidly that regions of the universe initially smaller than subatomic particles became larger than grapefruit in less time than it takes light to cross a proton. The expansion velocity exceeded the speed of light by factors so enormous that they challenge human comprehension of scale and speed. Cosmic inflation was driven by a hypothetical energy field called the inflaton, which created a form of anti-gravity that pushed space apart with exponentially increasing violence. Unlike normal matter that becomes diluted as space expands, the inflaton field maintained constant energy density, causing the expansion rate to accelerate exponentially during this primordial epoch. Think of cosmic inflation as the ultimate expression of exponential growth, where each tiny fraction of a second doubled the size of the universe. This doubling occurred roughly 60 times during inflation, creating a size increase equivalent to a single bacteria growing larger than the observable universe in the time it takes light to travel across an atomic nucleus. The inflaton field generated quantum fluctuations that were stretched to cosmic scales by the rapid expansion, creating the density variations we observe in the cosmic microwave background radiation. These quantum mechanical seeds, amplified by inflation, provided the initial conditions for all cosmic structure formation, including galaxies, stars, and planets. Inflation solves several puzzles about the universe's large-scale properties, including why distant regions that could never have communicated appear to have identical temperatures, and why the universe's geometry appears perfectly flat, despite the extreme sensitivity required to achieve this condition. The end of inflation occurred when the inflaton field decayed into normal particles and radiation, reheating the universe and initiating the hot Big Bang phase that standard cosmology describes. This reheating process converted the inflaton's energy into the matter and radiation that populate the universe today. Different regions of space may have exited inflation at different times, creating a multiverse where our observable universe represents just one bubble in an eternally inflating cosmic foam. Some regions might still be undergoing inflation today, generating new pocket universes with potentially different physical laws and constants. Gravitational waves generated during inflation should have left detectable imprints in the polarization patterns of the cosmic microwave background radiation. The detection of these primordial gravitational waves would provide direct evidence for inflation and reveal the energy scale at which this cosmic acceleration occurred. The rapid expansion during inflation stretched space so violently that it may have torn holes in the fabric of spacetime itself, creating topological defects like cosmic strings and monopoles that could still influence cosmic evolution today. Yet, even cosmic inflation's reality-stretching violence might pale before theoretical processes that could erase the very laws of physics that make inflation possible. Somewhere in the universe, a bubble of true vacuum might be expanding at the speed of light, erasing every atom, every law of physics, and the very concept of existence itself as it grows. This hypothetical catastrophe, called vacuum decay or vacuum metastability, could occur if our universe exists in a false vacuum state that appears stable but can suddenly collapse to a lower energy configuration. The transition would release so much energy that it destroys everything we know about reality, replacing our physics with entirely different rules. Vacuum decay begins with a quantum fluctuation that creates a tiny bubble of true vacuum somewhere in space. This bubble immediately starts expanding at light speed, its boundary representing an unstoppable wall of annihilation that vaporizes matter, energy, space, and time itself. Nothing can escape because the destruction propagates at the maximum possible speed. Think of our universe as sitting in a valley on a cosmic energy landscape, apparently safe, but actually perched on a false summit. A quantum tunnel could allow the universe to suddenly fall into a deeper valley, releasing gravitational potential energy equivalent to the mass of the entire observable universe, converted to pure destruction. The Higgs field, responsible for giving particles their mass, might exist in a metastable state that could decay to a lower energy configuration. Current measurements suggest the Higgs mass sits right at the boundary between stability and metastability, making vacuum decay a real possibility rather than pure speculation. If vacuum decay occurs, the expanding bubble would be completely invisible until it arrives, traveling at light speed with no advance warning. Stars, planets, and living beings would be erased from existence without even knowing the bubble existed until the moment of their complete annihilation. Inside the bubble, the laws of physics would be completely different. Particles might not be able to form atoms, fundamental forces could have different strengths, and the very concept of matter as we understand it might become impossible. The interior represents a realm where our current physics has no meaning or applicability. The probability of vacuum decay increases with high-energy processes that could provide the initial fluctuation needed to nucleate a bubble of true vacuum. Cosmic ray collisions, black hole evaporation, and hypothetical future particle accelerators could all potentially trigger this ultimate catastrophe. Vacuum decay events would be completely undetectable until they destroy everything within their reach. The expansion happens so fast that no information can travel ahead of the bubble boundary to warn potential victims of their impending erasure from reality. Some theories suggest vacuum decay could create new universes with different physics inside the expanding bubbles. Our own universe might have formed through vacuum decay in a previous reality with entirely different laws and constants, making us the products of someone else's cosmic catastrophe. The ultimate irony is that vacuum decay represents the most powerful possible event while being potentially inevitable. If our vacuum is metastable, then somewhere in the vast expanse of space and time, quantum mechanics virtually guarantees that fluctuations will eventually trigger the collapse. But perhaps even vacuum decay operates within a larger framework, where infinite universes ensure that every possible form of destruction and creation occurs simultaneously across reality's ultimate expanse. If the multiverse theory is correct, there are infinite copies of you reading these words right now, along with infinite versions where every possible variation of history, physics, and reality plays out simultaneously across dimensions beyond human comprehension. This cosmic ensemble contains universes where gravity repels instead of attracts, where time flows backward, where the speed of light is different, and where the fundamental constants that govern reality take on every conceivable value. Somewhere in this infinite expanse, every possible story has already been written, and every impossible dream has already come true. The multiverse emerges naturally from cosmic inflation, where different regions of space stop inflating at different times and develop into separate pocket universes with potentially different physics. Each bubble universe represents a distinct reality with its own space, time, and natural laws, completely isolated from all the others by the expanding walls of eternal inflation. Think of the multiverse as an infinite cosmic library where every possible book exists, including ones written in languages that don't exist, describing universes with completely different mathematics, and containing every combination of words that could ever be written. Our observable universe represents just one volume in this infinite collection of realities. Quantum mechanics suggests that every possible outcome of every quantum measurement occurs in parallel universes, creating an ever-branching tree of realities where all possibilities are realized simultaneously. This many worlds interpretation means that every decision you make splits reality into multiple branches, each one equally real and containing a version of you living out different choices. Some multiverse theories propose that mathematical structures themselves constitute universes, meaning that every self-consistent mathematical system corresponds to a physical reality somewhere in the cosmic ensemble. This mathematical universe hypothesis suggests that consciousness naturally emerges in mathematical structures, complex enough to support observers. The anthropic principle uses multiverse theory to explain why our universe appears fine-tuned for life, with physical constants that fall within the narrow ranges necessary for stars, planets, and complex chemistry to exist. In an infinite multiverse, every possible combination of constants occurs, and we naturally find ourselves in a universe compatible with our existence. String theory predicts that the multiverse could contain 10 to the 500th power different types of universes, each with unique combinations of particle masses, force strengths, and dimensional structures. This string landscape represents a cosmic parameter space, larger than the number of atoms in our observable universe. If parallel universes exist, they operate according to physics so alien that concepts like matter, energy, space, and time might have no meaning. Some universes might contain pure mathematical structures. Others might be composed entirely of information, and still others might exist as forms of reality that we cannot even conceptualize. The ultimate power in the multiverse belongs to whatever force or principle governs the creation and interaction of infinite realities. This metaphysical authority transcends individual universes, cosmic inflation, and even the concept of existence itself. The most humbling aspect of multiverse theory is that it makes our entire observable universe, with all its galaxies, black holes, and cosmic violence, nothing more than an infinitesimally small footnote in an infinite story of reality that encompasses every possible form of power, destruction, and creation simultaneously. We began this journey with solar flares that released the power of 10 billion nuclear bombs, thinking we had witnessed ultimate cosmic violence. Yet each step deeper into the universe revealed forces so much more powerful that they made the previous chapter seem gentle by comparison. From stellar explosions that outshine galaxies to black holes that bend reality itself. From dark energy tearing apart space-time to theoretical multiverse structures that dwarf our entire concept of existence. The most profound realization is that power in the universe operates on scales that transcend human imagination. A single neutron star collision releases more energy than our sun will produce in its entire lifetime. A gamma-ray burst can sterilize planets from across the galaxy. Dark energy commands the fate of cosmic expansion itself, while the multiverse encompasses infinite realities where every possible form of power plays out simultaneously. These cosmic forces remind us that we live in a universe far stranger and more violent than our daily experience suggests. The peaceful night sky masks a cosmic battleground, where matter and energy engage in conflicts so intense they reshape space and time. Black holes devour stars, galaxies collide across billions of years, and the fabric of reality itself might be unstable. Yet this cosmic violence also represents the creative force that makes our existence possible. Stellar explosions scattered the heavy elements needed for rocky planets and complex chemistry. Galaxy collisions trigger bursts of star formation that populate the universe with new solar systems. Even the Big Bang's primordial explosion created the space, time, and energy that would eventually become conscious beings capable of understanding cosmic power. The search for the most powerful thing in the universe reveals that power operates across every possible scale, from quantum fluctuations that might trigger vacuum decay to multiverse structures that encompass infinite realities. Each level of cosmic hierarchy contains forces that could destroy or create everything below it in the cosmic power pyramid. Perhaps the ultimate power lies not in any single phenomenon, but in the principle that governs how reality generates infinite forms of existence, destruction, and creation across cosmic space and time. The universe appears to be an engine for exploring every possible way that matter, energy, space, and time can interact, creating an endless hierarchy of power that stretches from subatomic particles to multiverse structures. The next time you look up at the night sky, remember that you're witnessing the gentle face of a cosmos engaged in constant battles between forces so powerful they make human conflicts seem like dust motes dancing in sunlight. We are temporary arrangements of stellar debris riding a small planet around an ordinary star in an unremarkable galaxy within a universe that might itself be just one bubble in an infinite multiverse foam. If you enjoyed this journey through cosmic power, subscribe to explore more of the universe's most incredible phenomena. What cosmic mystery should we investigate next? The universe has more secrets waiting, and some of them might be even more powerful than everything we've discovered so far.